Today we are going to discuss moment of inertia. What is moment of inertia? How we find moment of inertia of a point mass for the discrete distribution of mass and also for continuous body. Then we'll discuss what is the radius of gyration and what is its importance. Then we'll discuss theorem of parallel and perpendicular axis. We'll also see how we get that one. And after that, we'll try to find out moment of inertia of some bodies about different axes of rotation. After that, we'll do how we find moment of inertia of a body about a given axis. Just one or two examples we'll take, and we will basically apply theorem of parallel and perpendicular axis to the different cases where you want to find moment of inertia of a body about any given axis. So all these we'll discuss in today's discussion. Moment of inertia. It is the property of a body due to which it will resist any change in its rotational motion about a given axis. Just like as we have the inertia there for the translational motion or for the other cases there, where it was resisting any change in its state, whether it is the state of rest or of uniform motion about a straight line path. Here we have the moment of inertia, similar term is there and its role is also similar. It will resist now any change in its rotational motion about a given axis. Just like the inertia depends upon the mass of the body, moment of inertia of a body will depend upon the mass of the body as well as the distribution of the mass about the axis of rotation. So it will depend upon the two factors. So this moment of inertia for a given body about a given axis of rotation will depend upon two factors. One, mass of the body, and second is distribution of mass about axis of rotation. So it depends upon two factors. Now suppose we want to find moment of inertia of a point mass. So moment of inertia of a point mass, this one will depend upon the mass of the body, and suppose it is at a distance r, it is rotating about this particular axis of rotation. So this is the axis of rotation, and m is the point mass. M is the mass of a point particle which is at a distance r from the axis of rotation. So here this moment of inertia for the point mass, it will depend upon mass of the body and it will depend on a square of the distance from the axis of rotation. If you combine these two, then we'll get I proportional to mr square, or I will be equals to some constant into mr square. If we define the terms in such a way that k is 1, if terms are defined in such a way that k is 1, then what we'll get for I? This is your mr square. So that means moment of inertia of a point mass will be given as m into r square, product of mass and square of the distance of the point mass from the axis of rotation. So this is for point mass. Now if you take, suppose, moment of inertia of a discrete distribution of mass or masses. Like suppose this is your axis of rotation and we have a body where we have so many point masses. M1 is there at a distance r1, M2 is there at a distance r2, M3 is there at a distance r3, and so on. And it is rotating about this particular axis of rotation. So for this one, if you consider, it will be moment of inertia for the first point mass. If you take, it is your M1 r1 square. For the second one, it is your M2 r2 square, and so on. So it will just be added there. And we can write this as summation mr square. So moment of inertia for the discrete distribution of point masses. Remember, it is for the point masses. Here these are like the point masses. So you can get it as summation mr square. And if you now suppose apply this for a continuous body. So for continuous body, moment of inertia of a continuous body. This will be given as your I. Like suppose if I assume that it is just like summation mr square. So that means you have to take the product of point masses and the square of the distance from the axis of rotation. So here also for the continuous body, we'll take elementary masses there. We'll take at what distance they are located. And after that, r square dm integral of that will give the moment of inertia for this continuous body. Of course, for the integration, you will have to see how the masses are distributed for the given body and how you can apply that. So these will be the three main formulas for the moment of inertia of the point mass, discrete distribution of the point mass, and how we find moment of inertia for a continuous body. Now the unit of moment of inertia. Unit of moment of inertia. Since it is your mass and a square of the distance product, so in that case it will be kg meter square. So this will be the unit of moment of inertia. And what type of quantity it is? Is it a scalar or vector? Basically, moment of inertia is a tensor quantity. So it is a tensor. Tensor will be the physical quantity which will have the different values in different direction. Here also you can see when we'll take the different examples there, the moment of inertia of the same body has different values along different directions there. That means along the different axes there. So here, this one moment of inertia, we take it as a tensor quantity. But if just you have to distinguish between suppose scalar and vectors there, then in that case you may term that one as a scalar quantity. But in fact it is a tensor. Another term what we get here, that is called as the radius of gyration. This we normally represent by k. K is the symbol used for radius of gyration. This is basically the distance from the axis of rotation where whole mass of a body should be kept as a concentrated point mass so that it has same value of moment of inertia as that of the extended body about the same axis of rotation. So if you have to define, it is the distance from axis of rotation where if the whole body is kept as a concentrated point mass, then it will have same value of moment of inertia, same value of moment of inertia about that axis as that of extended body. That means if you have particular body, suppose I have a body here and this is suppose the axis of rotation. The moment of inertia of this body is suppose it is your summation mr square. Suppose we get it like that. In that case, if I put the entire body as a concentrated point mass, so this point mass, if it is kept at a distance k, which is the radius of gyration, then this will be equals to m into k square. That means moment of inertia will have the same value as that of the moment of inertia of the extended body about the given axis of rotation. Let's take one more example, then actual example, then it will be more clear there. Suppose I have a body whose moment of inertia is given as your 20 kg meter square. And its mass is, suppose it is your 5 kg. So moment of inertia is given as your 20. So I is your 20 kg meter square. And if I have to take the body whose mass is given as 5 kg and I have to put it as a point mass. So suppose I put that one as a point mass at a distance k. So this k should have the same value of moment of inertia as the given bodies about a particular axis of rotation. So it is your m into k square. Mass is given as your 5 kg, it is k square, or that represents k is equals to 2. It means this 5 kg mass should be kept at a distance of 2 meter so that you get the same value of the moment of inertia. It means the radius of gyration will be 2 meter there. Similarly, suppose you have a circular disc and its moment of inertia about its center of mass and perpendicular to its plane. This is your mr square by 2. This is the moment of inertia of a circular disc whose radius is r and mass is m. If I want to know what is the radius of gyration for this disc about this particular axis, in that case we'll write it as your mk square. So this will give you the value as k equals to r by root 2. It means that particular circular disc of mass m, if I put that one as a point mass, then it should be kept at a distance r by root 2 so that you will have the same value of moment of inertia. So for given cases, if moment of inertia value is given, simply use the formula I is equals to mk square and compare it with the given value of the moment of inertia. You will get the value of the radius of gyration. And then what will be the unit of this radius of gyration? Unit of radius of gyration. Since it is simply the distance, so in that case unit will be meter. In SI system if you take, so its unit will be meter. There are two theorems in moment of inertia. One is theorem of parallel axis and other is the theorem of perpendicular axis. If you know the moment of inertia of a body about its center of mass, then you can find moment of inertia about any axis using the theorem of parallel and perpendicular axis. So let's first of all take what is this theorem of parallel axis and what is theorem of perpendicular axis, and then we'll apply it to find moment of inertia of any given body about any given axis. So this says theorem of parallel axis that the moment of inertia of a body about a given axis is equal to sum of moment of inertia of the same body about a parallel axis passing through its center of mass and product of mass of the body and square of the distance between the parallel axes. Like here, suppose we have a body, it is this particular body, and this is suppose the axis which is passing through its center of mass. So its center of mass is here, this is suppose the axis, and this is the axis about which we want to find moment of inertia. So moment of inertia about this axis is suppose I there. This is the axis about which we want to find moment of inertia, and moment of inertia value is I. And moment of inertia about a parallel axis, these two axes must be parallel to one another, and passing through its center of mass is suppose your I naught. We assume that m is the mass of the body and the distance between these two parallel axes is h. So we get mathematical expression for the theorem of parallel axis as I equals to I naught plus mh square. Again, I is the moment of inertia of the given body about a particular axis. I naught is moment of inertia of the body about a parallel axis and passing through its center of mass, and h is the distance between the parallel axes. So this is suppose the mathematical expression, and let's see how we get that one. For that, let's assume that we have a point mass, a small m, at a distance x from the center of mass of the body. So moment of inertia of point mass, a small m, about, suppose I take this as AB and this is your A dash B dash. So moment of inertia about AB. This is the axis about which we want to find moment of inertia. So this will be equals to how much? M into x plus h whole square, because now the distance of this point mass from this axis of rotation will be your x plus h. So this is the moment of inertia. Now if you want moment of inertia of the entire body about AB, in that case it will be just the summation of this one, x plus h whole square. This can be written as your summation mx square plus h square plus 2xh. We have simply expanded this a plus b whole square there. Now this is your summation mx square plus, now h is constant, so I can take it outside this summation sign. So it is your summation m plus, again h is constant, rather 2h is constant, so it is summation mx. This is the expression. Now this term summation mx square, x is the distance from the center of mass of this body. So if you take summation mx square, it means you will get the moment of inertia about its center of mass. So this will be your I naught. Then this is your h square summation m, algebraic sum of all the point masses which is constituting this body. This will be equal to m. Then this term 2h summation mx, this term will be 0. Why it is 0? Because we are taking algebraic sum of distribution of mass about the center of mass. Remember the definition of the center of mass, what we have how we have defined that. Center of mass is the point about which the mass of a body is assumed to be uniformly distributed. So if you take algebraic sum of the distribution of the mass about the center of mass, then this term will be 0. So you can write as algebraic sum of distribution of mass about center of mass of a body is 0. Now why it is 0? because the mass is uniformly distributed about the center of mass. As mass is uniformly distributed about center of mass, so that term will be 0. So here, if you consider this is how much it will be, your I naught plus m h square. This is your mathematical expression and it is the proof of that. So this is how we can get this mathematical expression for theorem of parallel axis derived or proved. One thing you can take for this part, if it is you are getting any confusion how we get that one, we have taken the algebraic sum of the distribution, okay, about the center of mass, and we say that it will be 0 because it is uniformly distributed. Just in other term, if you consider, we take the numbers like 1, 2, 3, 4, okay, and we are taking it up to 9, okay. So it is your 4, 5, 6, 7, 8, 9. This is suppose your x. If you consider their mean value, how much will be the mean of this distribution? This will be 5. Okay, so it will be 5 there. And now if you consider the difference between x and x bar, that means what you are taking, it is the deviation from the mean value. Just like it was your summation mx, that means how the mass is located from the center of mass there. So here if you consider x minus x naught, this is how much? This is minus 4, this is minus 3, 3 minus 4, in that case it is your minus 2, this 4 minus 1, that is your 1, this is 0 for 5, for 6 it is your plus 1, plus 2, plus 3, plus 4. And now if you take this summation delta x, this will be 0. Why? Because you have taken algebraic sum of the distribution about the mean value. Instead of this mean value, if I choose any other number, say we take 4. So if it is taken as x minus 4 for all the data, then that sum will not be 0. It will be only 0 in that situation when you are taking the distribution about the mean value. So here also, if you take the algebraic sum of the distribution of the mass about the center of mass, then it will be 0 because it is uniformly distributed about center of mass. Just like here, this data is uniformly distributed about the mean value. If you take any other assumed mean, there the deviation will not be 0. Algebraic sum of those deviations will not be 0. Let's take a theorem of perpendicular axis. The sum of moment of inertia of a uniform lamina about two mutually perpendicular axes lying in its plane is equal to moment of inertia about the third axis perpendicular to the given axis and passing through the common point. It means we are taking sum of the moment of inertia about two mutually perpendicular axes lying in the plane of a lamina. This will be equal to moment of inertia about third axis, which is passing through common point of the two. For this one, suppose I take this as a lamina. This is the lamina, and we consider that there are two mutually perpendicular axes. Like suppose this is your x-axis, this is your y-axis, and this is your z-axis. So what we say that these three, you can see that they are mutually perpendicular and two of them are lying in the plane of the lamina. Remember one thing, this is applicable for a lamina, for laminar bodies. If the body which is given is not a laminar one, in that case you cannot apply. It's not that about any two mutually perpendicular axes you can take the sum of the moment of inertia. The two mutually perpendicular axes must lie on the plane of a lamina. So for that only you can apply. So suppose for this one, I assume that we have a particular point P having coordinate xy. And here we have a point mass M. So we drop a perpendicular on x-axis and y-axis. So suppose this is the perpendicular dropped on y-axis and this is the perpendicular dropped on x-axis. So this is suppose your P and this is your suppose Q and this is your R. And this is your OP. Now obviously if you say that this is perpendicular, that means this distance will be how much? It is y and this distance will be x, because this one in respect to the x-axis its distance is x because coordinate we have taken as xy. So moment of inertia of point mass about x-axis, this will be equals to how much? It is your m into pq square, that will be equals to m into y square. Therefore moment of inertia of entire body or entire lamina about x-axis, this we represent it as your IOX, so it will be your summation m y square. Similarly, moment of inertia of the body about y-axis, this will be how much? It will be summation mx square, because this x is the perpendicular distance from the y-axis. Therefore, if you take the sum, moment of inertia about x-axis, moment of inertia about y-axis there, this will be your summation my square, summation mx square. And this will be equals to how much? Summation m we can take outside. This is now y square plus x square. How much is this y square plus x square? This is your x, this is your y. So how much it will be? This will be equals to summation m op square, this distance. And if I assume it that this is at a distance r, in that case this will be your summation m r square. OP is the distance of the point mass from the z-axis there. So in that case it is your summation mr square, and this is nothing but your moment of inertia about z-axis. So we have got that moment of inertia about x-axis plus moment of inertia about y-axis. This is equal to moment of inertia about z-axis. Remember, x and y, it is just a symbolic representation for representing the moment of inertia about two axes which are mutually perpendicular. It need not be that the moment of inertia we want about x-axis and about y-axis. Second thing, it is there applicable for a laminar body or for a lamina. Third thing, the two mutually perpendicular axes which we have taken, it must lie on the plane of the lamina. And the fourth point, the third axis which we are taking must pass from the common point. If suppose x and y have a common point here, in that case it should pass through that and it should be perpendicular to that given two axes there. It's not that if I take the axis somewhere here and sum of the moment of inertia about x and y will be equal to moment of inertia about this. It is not passing through the common point, although it is perpendicular to the two. So these things you just remember for application of the theorem of perpendicular axis. Suppose we want to find moment of inertia of a uniform rod about an axis passing through its center of mass and perpendicular to its length. In fact, we are just trying to see how we can find moment of inertia of a continuous body. We'll assume that this is suppose a thin uniform rod, and we want its moment of inertia about an axis which is passing through its center of mass and is perpendicular to its length. So this is suppose the axis, this is suppose your PQ, and AB is suppose the rod. Its mass is suppose m, and length we take it as L. of the thin rod. Remember, moment of inertia of a body about different axes which is passing through different points, or even if you take for particular axis there, depending upon its orientation, the moment of inertia value will be different. So whenever it is given that you have to find moment of inertia or you have to write the value of the moment of inertia, don't just see for the body, for which body you want to find moment of inertia, but also see from where the axis of rotation is passing. Because depending upon the position of the axis of rotation and its orientation, the moment of inertia of the same body will be different. So here we are taking that it is passing through its center of mass and it's perpendicular to its length. Let's suppose we take an elementary section. This is suppose at a distance x and its thickness or length is your dx. So for this rod, mass per unit length, this is equals to m by L. Now we can take a mass of elementary section. What we have taken this one. This is how much? M by L into dx. This is mass per unit length and we have multiplied it by the elementary length there. Remember one thing. If this is your thin uniform rod and you are taking a very thin section of it, a very fine slice of it, in that case, how it will look like? It will look like a point mass. And moment of inertia of the point mass about a given axis, what was that expression? It was your mr square. So treating this elementary section as a point mass, moment of inertia of elementary section about PQ, that is the given axis, this will be equals to m by L dx into x square. It is basically x square dm you can say, or it is dm into x square, it is written here. So moment of inertia of entire rod about the given axis, that means about PQ, it will be m by L x square dx integral. And what will be the limit of integration? If you take the variation of x, it is from one end to other end. That means the elementary section can take position one at A, other at B. So when it is at A, it is your minus L by 2. When it is at B, it is your plus L by 2. So in that case, this one will be equals to m by L x cube by 3. Limit is your minus L by 2 to plus L by 2. So this is your m by 3L. And for x, I am putting L by 2, that is the upper limit, L by 2 whole cube minus L by 2 whole cube, that is the lower limit here. And this, if you simplify, it is your m by 3L. This is your L cube by 8 plus L cube by 8. And this is your ml square by 12, because it will be your L cube by 4. So one L will get cancelled, you will get ml square by 12. So this is the moment of inertia of the body, that is the thin uniform rod, about an axis passing through its center of mass and perpendicular to its length. For the same rod, if suppose we want to find moment of inertia about an axis passing through its one end and perpendicular to its length, that means this time the axis is not passing from this point, but it is passing from one end of it. So suppose this time we take that axis is passing from this point. So this is your axis PQ. So in the same way we'll proceed. We have taken the elementary section. Suppose this is the distance x now, this is your dx. And now again in the same way, if you take mass per unit length, it is your m by L, mass of elementary section m by L into dx. Moment of inertia of the elementary section about PQ, it will be dm into x square. Moment of inertia of the entire rod about this particular axis, So it will be the same, you have to integrate. Now what change will be there? It will be the change in the limit there. So now the lower limit, as it is passing through one end, so lower limit will be 0, because one extreme position of the elementary section will be at this end, other will be at the other end. So when it is here, it is 0 and this is your L. So this will be your 0 and this is your L. So this is your m by 3L, L cube minus 0, and that is equals to mL square by 3. This is the expression for moment of inertia of the thin rod about an axis passing through its one end and perpendicular to its length. So we have derived expression for moment of inertia of a thin rod about an axis passing through its one end and perpendicular to its length. Let's now apply theorem of parallel axis there to get this value of moment of inertia, because we have already seen what is the expression for moment of inertia of the thin rod about an axis passing through its center of mass. So let's apply that theorem of parallel axis there. Basically, it is an alternative method there. Using theorem of parallel axis, we want moment of inertia about this axis, that is about its one end. So we'll take a parallel axis passing through its center of mass. So this is suppose the axis passing through its center of mass. This is suppose your P dash Q dash. So use and what is the basic formula? I equals to I naught plus mh square. We want moment of inertia about PQ. So we'll take moment of inertia about its center of mass about an axis which is parallel to the given axis. So this P dash Q dash is parallel to PQ. So this value will be equals to mL square by 12. We have derived this expression. Moment of inertia of thin rod about its center of mass and perpendicular to its length. This is now m, and the distance between these two parallel axes, how much it is? Entire length is your L, so this is your L by 2. So this is your m into L by 2 whole square. So this is your mL square 1 by 12 plus 1 by 4, and this is equals to mL square, if you take LCM, 1 plus 3, and that is your mL square by 3. This is exactly the same expression which we have derived directly by using integration. This is the expression which we have derived. So this way you can find moment of inertia by using theorem of parallel axis. Only thing is that you should know what is the moment of inertia of the given body about its center of mass, and that is also about a parallel axis. So you can use theorem of parallel axis there to find moment of inertia about any given axis. If suppose it is asked that it is a 1 meter long rod, and what will be the moment of inertia when it passes through 1/4 of its length from one end. Or suppose it is a meter scale, it passes through 25 centimeter mark and it's perpendicular to its length, or 60 centimeter mark there. So that way you can easily apply. These are the moment of inertia of different shaped bodies about their center of mass. You should know this one, and if you know this value of the moment of inertia about their center of mass, then using the theorem of parallel and perpendicular axis, you can find moment of inertia of this body about any axis. So like if I take the moment of inertia of a uniform thin circular ring about an axis passing through its center of mass and perpendicular to its plane, that will be your mr square. M is the mass of the ring and r is its radius. Similarly, if you take the thin circular disc and it is about its center of mass and perpendicular to its plane, then it will be your mr square by 2. If you take solid sphere and moment of inertia is about its center of mass and perpendicular to its length, so suppose this is the solid sphere, mass is m, length is L, radius is r, and we take the axis passing through its center of mass. So this value of the moment of inertia is mL square by 12 plus r square by 4. Similarly, if you take the moment of inertia of a solid sphere about its diameter, it is 2 by 5 mr square. For hollow sphere, it will be your 2 by 3 mr square. R will be the radius there and m will be the mass. Let's apply theorem of parallel and perpendicular axis for few more cases there. Then it will be more clear. Suppose I want to find moment of inertia of a thin circular disc about its diameter. We want to find moment of inertia of the thin circular disc about its diameter. Suppose this is the circular disc and mass is m, radius we are taking it as r. We'll take two mutually perpendicular diameters. Suppose this is your d1 and this is your d2. These are mutually perpendicular. And moment of inertia about the diameter, if I assume that it is it. Remember, for a uniform circular disc, and we are taking suppose two mutually perpendicular diameters, the diameters will be the identicals. You cannot distinguish one diameter from the other one. So obviously the moment of inertia about the diameter, whether you take d1 or d2, it will be same. So it is suppose id. So we take the moment of inertia about the diameter is id. Now we take third axis, which is perpendicular to these two. Now remember, the diameters will be lying in the plane of the circular disc. So that means it is lying in the plane of the lamina there. So this is the axis which is perpendicular to these two diameter. That means it is basically perpendicular to the plane of the disc. So there the moment of inertia is I. So it is passing through its center of mass and perpendicular to its plane. So in that case, using theorem of perpendicular axis, where you have IOX plus IOY, this is your IOZ. So about one diameter, about the other diameter, the sum of these two moment of inertia will be equal to moment of inertia about third axis, which is perpendicular to these two. So this is how much? This axis is passing through its center of mass. So for circular disc, it was your mr square by 2. So 2id is mr square by 2 and id will be equal to mr square by 4. So this is the moment of inertia of the circular disc about its diameter. Let's take another case. We want to find moment of inertia of the thin circular disc about its tangent. And the tangent is, in one case it is parallel to its diameter and in another case it is perpendicular to the diameter. So suppose if I take that this is the circular disc, tangent is parallel to the diameter. So that means this is suppose the tangent here, and this is suppose its diameter. This is I. Now here in this case we'll apply the theorem of parallel axis this time, because this is, we know the moment of inertia about the diameter, and this axis about which we have to find moment of inertia, this is parallel to its diameter. So using theorem of parallel axis, you will get moment of inertia I equals to moment of inertia about its diameter, because in place of I0 it is your id here, plus m. What is this distance? If the radius is r, it is your mr square. So this will be equals to mr square by 4 plus mr square, and that is your 5 by 4 mr square. So this is for the first part. For second one, where the tangent is perpendicular to its diameter, it means if suppose this is the circular disc and the tangent is perpendicular to its diameter, that means it is perpendicular to its plane. So now we'll take the axis passing through its center of mass and perpendicular to its plane. So this is the axis which is passing through its center of mass, and this is the axis about which you want to find the moment of inertia. This is the tangent. Here also this was your tangent, and this is the diameter. And this is now the axis passing through its center of mass. So this time again we'll use the theorem of parallel axis. So here this distance is again r. So this I will be equals to I naught plus mr square. But this time the moment of inertia of the disk about its center of mass and perpendicular to its plane, this is your mr square by 2. This is your mr square, and that is your 3 by 2 mr square. Suppose we want to find moment of inertia of a solid sphere about its tangent. So for that, suppose this is the solid sphere and we want it about this axis. This is suppose its diameter, and we have got the expression for the diameter as id. This is your I which we want to find. So again, using theorem of parallel axis, I will be equals to I naught plus mh square. Now the moment of inertia about the diameter of a solid sphere, this is your 2 by 5 mr square. This is your mr square. R is the distance between the two. So this is your 7 by 5 mr square. This is the expression for moment of inertia. So this is how you can find moment of inertia of any body about any axis using the theorem of parallel and perpendicular axis, if you know what is the moment of inertia of the body about its center of mass.